We could break the crust down into two distinct parts, oceanic crust and continental crust. And as you can see right there in red, the oceanic crust is about 5 to 7 kilometers thick. Not a lot of variation when it comes to oceanic crust. The 7 kilometer thick areas are probably where volcanic islands like Hawaii stick out of the oceanic crust. So that's where you're going to find a thicker oceanic crust. Now, for the continental crust, you can see 10 to 70 kilometers thick. That's really, really thick when it comes to crust for 70 kilometers. Now, where are you going to find 70 kilometers? The Himalayas, basically a mountain range sitting on top of a convergent continental convergent boundary. Most places is not going to be 70 kilometers thick. The basin and range, the whole western United States, in between the Rockies and the Sierra Nevadas, all of that area is being stretched out and thinned and being pulled apart. And so the continental crust in this whole basin range area is actually becoming thinner over time. Now, oceanic crust, mostly basalt. If you know anything about basalt, it's darker, heavier, contains more metals, whereas the continental crust contains more granites. And if you have granite countertops, you've probably seen granite. It's pinker, lighter, it's got whiter materials in it like quartz. And because of that, it has less metals and it's less dense than basalt. The crust is the least dense layer, and that's probably why it rides on top of the lower layers like the mantle. So that's probably why it floats on the mantle, because it is less dense. Now, you've probably heard of plate tectonics before. There's something like 9 to 14 major tectonic plates. They float on top of the mantle because they're less dense. They run into each other. They slide past each other. Some of them sink under each other. It just depends on their density. That's what affects pretty much everything with tectonic plates. Also, the least dense layer. They're also the coldest layer as well. We live on the crust. It's not that hot, at least not that hot on the surface of the crust. As you go farther down, though, things do heat up a little bit. Now, mantle, largest layer, thickest layer, deeper than the crust, more dense than the crust, but also more melted than the crust. So the mantle, while mostly solid, like hot asphalt or even warm candle wax, the mantle is able to move around if pushed. And so you can see the temperature of the mantle right there, 1,000 Celsius up to 3,700 Celsius. That's pretty hot. If you think of lava that comes out of a volcano, 3,700 Celsius is way hotter than lava that comes out of a volcano. 1,000 is a little bit colder than most volcanic lava, but it does cool down eventually to 1,000. So yeah, temperature-wise, big variation. 1,000 is closer to the crust, while 3,700 is closer to the core. Now, a few other things about the mantle. As you go farther down the mantle, density increases. You can see that in the graph right here. Depth below surface, as you go from the upper mantle to the lower mantle, density over here on the y-axis increases. Why? Well, one, there's more metals as you get closer to the core, metals that sunk when Earth was first forming. And metals, like the silver right here, are definitely more dense than rocks. Now, the other reason is it is made of rocks, mostly in the mantle, and as you squeeze rocks more and more, those rocks will take on different shapes that allow them to become more dense. It's like if you took popcorn and you squeezed freshly popped popcorn, it wouldn't retain its fluffy shape. It would become more and more dense as you crushed it more and more. Same thing with rocks. I mean, they're pretty dense to begin with, but you can squeeze them further into more dense shapes. Now, let me ask you this. Why? Going back. So that mantle magma that rises up through the asthenosphere hits this lithosphere. So all this stuff up here, lithosphere, because see, it's brittle up here. It can't move. Plastic down here means it can move. So that's where the convection currents are moving through the asthenosphere. Now we go back down here. Where are you going to get convection currents? You're only going to get convection currents where the rocks can move. And that's not going to be in the lithosphere because the lithosphere is solid. Heat transfer by circular movement only works in liquids, gases, plasma, and in the mantle where it's plastic enough to move. So warm rock, it warms it up enough to actually move it around. Once that warm rock hits solid rock, so brittle rock, rock that's cool enough not to move, it can't move up anymore and it has to move to the sides. So that's why convection currents move to the side, the tectonic plates. They can't break through the continental crust in most cases. They just hit it, move to the side, and then fall back down again and sink when they're colder. So just like a hot air balloon, man. So lithosphere, brittle, solid. It cannot be broken through by convection currents in most cases, whereas the asthenosphere, convection occurs inside the asthenosphere. So that is where convection occurs. That is where more mantle magma rises up and pushes around the lithosphere, which is the tectonic plates. Sometimes it breaks through at mid-ocean ridges. Most of the time it doesn't. Okay, now we're to the core. So the core, two parts, outer core, inner core. Outer core is mostly made of nickel and iron, but actually so is the inner core. The outer core is liquid. That is the big difference in the inner core. You can see it right there. It is molten liquid metal. It provides the heat for the mantle. It's pretty hot in the outer core, 4,700 Celsius or 8,500 Fahrenheit, and about 2,300 kilometers thick. Let's go and take a look at the inner core. Notice the difference in temperature between these two. So ready? Outer core, 4,700 Celsius. Inner core, 6,650 Celsius. So almost 2,000 degrees hotter Celsius than the outer core. Pretty hot. It's also thinner than the outer core, only 1,200 kilometers thick. And I mentioned earlier, it's responsible for generating Earth's magnetic field. The inner core does not spin at the same speed that the Earth spins at. It spins at a different speed. And because the inner core spins at a different speed than Earth, and because it's made of iron, it gives us a dynamo effect. It kind of makes a weak magnetic field, which allows us, to have compasses that work on Earth. The magnetic field just protects the atmosphere from being stripped away. Now, another interesting thing about the inner core is because the inner core is growing, it's growing by taking away from the outer core. So actually, overall, Earth is actually shrinking because the inner core is growing. So what's happening, if I could back it up a slide, is the outer core right here, some of this liquid outer core, every single day, some of that liquid outer core actually sticks to the inner core and becomes solid. And when you turn a liquid into a solid, heat is released. So the inner core grows, the outer core shrinks, and it gets heated up because it's becoming more solid. Why does it become a solid even though it's like 6,000 Celsius? Pressure. Lots of pressure. Normally it would be a liquid on our surface, but the whole Earth is squeezing down on the inner core, making it solid. Okay, I think that's it for the inner core. Let's get to our first